This presentation is part of the TI-Nfocus AP Calculus video series. In this video, I'll discuss some technology solutions and problem extensions for the 2017 AP Calculus exam, free response question BC2. My name is Steve Kokoska. I'm a professor at Bloomsburg University in Pennsylvania, and I'm a former AP Calculus chief reader. Here's an outline of the information presented in this video. I'll start by reviewing the free response question, and then the scoring guidelines used at the AP Calculus reading. And I'll focus on the solutions presented in these guidelines, not how the points were awarded. This free response question was calculator active, so I'll show how to use technology to explore and solve parts of this question where appropriate. And because the free response questions are usually very comprehensive, I'll suggest some problem extensions, additional AP Calculus type questions associated with the information given in the problem. And some of these questions may be calculator active. In this problem, we're given the equations for two polar curves and their graphs. The regions R and S in the first quadrant are defined using these polar curves as boundaries. In part A, we need to find the area of the region R. In part B, there is a ray theta equal k that divides the region S into two subregions of equal area. Students were asked to write an equation involving one or more integrals whose solution gives the value of k. In part C, the function w of theta represents the distance between points on the two polar curves. Students were asked to write an expression for w of theta and to find the average value of this function over the interval 0 to pi over 2. In part D, students were asked to find the value of theta such that w of theta equals the average value found in part C. And finally, students needed to determine if this function w of theta is increasing or decreasing at this found value of theta. Here's a quick look at the scoring standard used at the AP Calculus reading. And remember, I'm going to focus on the solutions here, not how the points were awarded. Part A was worth 2 points. Remember, this is a calculator active question. So 1 point for the integral, the mathematical expression using correct notation, and this includes the bounds, and 1 point for the numerical or analytical answer. Part B was worth 2 points. 1 point for an integral expression for one region where one limit is k. For example, this expression, or this expression. And 1 point for everything else. That is the final correct equation. Part C was worth 3 points. 1 point for a correct explicit expression for w of theta, 1 point for the integral expression in the formula for average value, and 1 point for the actual average value. Part D was worth 2 points. 1 point for solving the equation w of theta is equal to the average value, for finding the value of theta such that w of theta equals the average value found in part C. And 1 point for stating that w of theta is decreasing at this found value of theta, and for providing a valid reason. To find the area of the region R, we need to use the formula for the area of a polar region. And I used the TI-Nspire to solve this problem. On a calculator page, I defined the function f, and then I evaluated the definite integral for area. Note that the TI-Nspire CX-CAS calculator returns the exact symbolic answer here. To find the numerical result, I used the approximation function. Or I could have included a decimal point in one of the constants in the integral expression. For example, I could write the constant in front as 1 point divided by 2. Here's an extension to this question involving the functions f and g and a circle of radius 1. First, find the area of the region in the first quadrant bounded by the curve r equals g of theta and the x-axis. And find the area of the region in the first quadrant inside the graph of r equal f of theta and outside the circle r equal 1. In part A, I need to use the formula for area of a polar region. And I'm going to solve this problem analytically before considering technology. So I use the expression for the function g, and then the half-angle formula. I can then integrate term by term. Evaluate this antiderivative at the upper and lower bounds, find the difference, and the area of the region is pi divided by 2. It's pretty easy to find this solution using technology. On a calculator page, I defined the function g, and then I evaluated the appropriate definite integral for area. The result is the exact symbolic answer, pi over 2. To solve part B of example 1, I first tried to visualize the region of interest. The shaded region here is inside the graph of r equal f of theta and outside the circle r equal 1. In order to find the area of this region, I need to find the point of intersection of the two graphs. So I set f of theta equal to 1 and I solved for theta. I used the principle of zero products and the fact that theta must be in the first quadrant. So the point of intersection is 1 pi divided by 4. Here's a mathematical expression for the area of the region of interest. I need to find the area inside the graph of r equal f of theta and subtract the area inside the circle. Using technology, here are the graphs of the two polar curves of interest. And here is the exact symbolic answer. That's pretty cool. And the numerical approximation. In part B of the free response question, we need to write an equation that gives the value of k such that theta equal k divides S into two equal subregions. Here's the first solution given in the scoring guidelines. Although the free response question did not ask for the value of k, we can use technology to find it. I first found the value for C, the area of the region S. Then I used the solve command to find the value of k. And here's a visualization of this result. In part C, we need to find the average value of the function w of theta over the interval 0 to pi over 2. Here's the mathematical expression for the average value. Using technology, I defined the function w, and then I found the average value, 0.485. And using technology, here's a nice visualization of this result, of the average value in general. The shaded area, the area under the graph of w from 0 to pi over 2, is equal to the area of the rectangle with width pi over 2 and height 0.485. In part D, I need to solve the equation w of theta is equal to the average value found in part C. I used technology to solve this equation, and I stored this value in the variable, or really a list of length 1, named d. And then I found the derivative of w at the first and only value in this list, d sub 1, or really the first entry in the list d. Since this derivative is less than 0, w of theta is decreasing at theta equal 0.518. Here's another problem extension using the information given in the free response question. Now, even though this topic is not in the curriculum framework, I think this problem is a nice extension and it demonstrates a good use of technology. Find the length of each polar curve. First, recall the formula for the length of a curve described by a polar equation. I have the expression for r, and I can find dr d theta. But I don't think I can find the symbolic antiderivative in the expression for L. So using technology, the length of the polar curve described by r equal f of theta is 2.168. Similarly, the length of the polar curve described by r equal g of theta is pi. You might try to find this answer analytically. And I think there's a simple geometric argument to justify this answer also. And here's one more problem extension involving the polar curve r equal g of theta. First, show that the Cartesian equation for this polar curve is a circle centered at 1, 0 with radius 1. Show analytically the result in example 2. That is, that the length of the polar curve for theta between 0 and pi over 2 is pi. And finally, find analytically the area of the region in the first quadrant bounded by the polar curve described by r equal g of theta. I hope this video gives you some good ideas for additional practice AP Calculus exam type questions and of how to use technology to solve some of the parts of this problem and to explore, confirm, and visualize results. And just a reminder, there are lots of valuable resources on the TI website. There is material there involving technology and calculus, classroom activities, and lots of calculator tips and tricks for test success.